Hello, and welcome to What's on Board, our insider's look at some of the science headed to the space station tomorrow. I'm Stephanie Shearholtz from NASA's Office of Communications. Tomorrow, the Cygnus spacecraft from Northrop Grumman is scheduled to launch at 9:59 a.m. Eastern Time on its 12th commercial resupply services mission. It will carry about 8,200 pounds of research, supplies, and hardware to the orbiting laboratory and the crew of 6 who are living there. In the next hour or so, we're going to learn more about some of the science that is part of that payload. The International Space Station is one of the most unique laboratories we have and a great place for scientists to conduct research. These investigations are helping us to learn what we need to move farther into space, to go to the moon, land the first woman and the next man there as part of NASA's Artemis lunar exploration program, and travel on to Mars after that. The knowledge also comes back to us and helps us with technological advancements that improve our lives here on Earth. First, we'll talk to our science experts about an overview of what's on board NASA's exploration to advance NASA's exploration efforts, and the science conducted as part of the International Space Station's U.S. National Laboratory on the space station. Following our brief introduction, I'll introduce each of our speakers to talk about their specific science or technology payload, and you'll have the opportunity to ask them questions about what they're sending and what their experiment or investigation is covering. So use the hashtag AskNASA to send in your questions, and we'll take them after we also take questions from the room. So first off, we'll hear from Pete Hasbrook. Pete is the manager of the Program Science Office for the International Space Station program. Pete, over to you.
Thank you, Stephanie. Thank you all for coming today. It's great to see you all, and thank you to everybody who's tuned in on NASA TV and other places. We are really, really glad to be here. We're glad to share the science with you and the scientists with you in many cases for the Cygnus launch that's scheduled for tomorrow morning. The Cygnus vehicle and our other visiting vehicles are very important to us, especially from the science perspective. This Cygnus is bringing science cargo that is supporting over 30 experiments that are either just going to start on the ISS or have already been ongoing. They will join experiments for the next 6-month period of what we call the Expedition 61 and 62 phase. During this time, we'll have at least, we'd say, about 250 experiments. Often it's over 300 experiments going on at any one time. Our National Lab representative, who's speaking after me, will tell you a little bit more about some of those experiments. You may know that this is the Cargo Resupply Services number 2, first delivery, CRS-12, the first time that the Cygnus will be operating fully under those contract parameters for us. And that's really important to us in the NASA world and in the science world because of several improvements in the Cygnus vehicle, the Antares rocket as well. They've implemented some of those already, but this is the first time we get the full suite. Some of those improvements are increased mass and volume for the cargo that we bring to station, all of our cargo, not just for research. We get more powered lockers, as we call it, in the vehicle for the launch. The powered lockers are very important to us for the cargo and the scientific work that needs power, that needs cooling, that needs thermal. During the delivery phase up to the ISS, it needs continuous power. We get the benefit of later cargo loading in the Antares and the Cygnus processing. We get to load more cargo. It's in 3 different phases. It's closer to the launch, which again is very important to some of the science that has very short life or short time to the start of its science. We also have better telemetry. We have telemetry for the experiments that are going up, so we know how they're doing during the time between launch and the arrival at the station. And finally, a good feature for us is now the disposal of some of our external instruments and payloads from the ISS. That gives us more flexibility for swapping payloads on future vehicles. We'll talk a little bit of history for a moment. Tomorrow, November 2nd, we start the 20th year of the ISS and human presence in space. That means for many years now, 1/4 of the Earth's population, who are 18 and under, some 19-year-olds now, have never lived in a time where we didn't have humans living and working in space on the International Space Station. So we've been looking forward to that for a long time. And through the course of the next year, you're going to see stories and features about the science that we've done over the course of our history. A little bit more history, we always like to give the statistics over the course of the ISS. So through March of this year, we've done over 2,700 different experiments on the ISS, and that's across our international partnership. We've served more than 4,000 scientists. We've had 108 countries who have participated in some way, whether through traditional research or through educational activities. And we've had, we know of, more than 1,700 different scientific peer-reviewed publications that are talking about the research and what's been accomplished on the ISS. But we don't just look backward, we look forward. As Stephanie mentioned, we have the Artemis program, and we are going to the moon. We're going to land on the moon by 2024 with the first woman and the next man to land on the moon. The ISS has been supporting this kind of an effort and exploration for all of our 20 years, not just with the humans in space, but since we launched our first elements. We have really two aspects to that. We study human research. We study and learn how to keep our humans safe and healthy in space. And some of the areas that we focus on are bone and muscle loss, vision effects, health monitoring, remote health monitoring and care, and physical and mental function. And on the technical side, we demonstrate technology for things like advanced life support systems, for fire safety, for operations. And indeed, operations, our international partnership of the ISS is a great model for going to the moon, for the Gateway program, for future international cooperation, not just at the operations level, like flight control teams and astronauts, which you see, but also the governance model. We are a treaty, international treaty in space, and that is the model that we're going to use as we go forward to the moon and go on to Mars from there. So to wrap this up, we have a few products that I'd like to share with you. I hope you know about. We write stories. Our program science office writes the stories that go on nasa.gov about science. You can subscribe to those. That's one of my favorite things. To subscribe to that listserv, I want you to repeat after me. go.usa.gov/26UE. See how short that is? If you want to subscribe, we send you a weekly digest every week about the stories that have been happening in the past week, as well as the things that we're featuring. And we also have an app for that. On your iPhone or your Android device, we have an app in those stores. It's called the Space Station Research Explorer. It has details about all the research that we've done, especially what's upcoming. Space Station Research Explorer. We'd love to have you join us. We also would love to have you follow us on Twitter, ISS_research. And with that, I want to transition to our next speaker, a longtime friend and partner in science, and a senior associate scientist for the ISS National Laboratory, Dr. Liz Warren.
Well, thank you, Pete, and thank you to this big audience for being here today. As I'm sure you're already aware, you are in for a really great launch, and today we're going to tell you about a lot of research. So I'd like to say, yesterday was Halloween, but really all the treats are yet to come. So the International Space Station is an absolutely phenomenal place to conduct research, and it is an ISS U.S. National Laboratory. That means it is open to users from academia and industry and other government agencies. And those users choose to do their space research in a very unique environment. And they're doing that to bring some benefit back to Earth. So that's really the mission of the ISS National Laboratory. While NASA is focused on exploration initiatives and learning how to live in space longer and keep equipment functioning longer in space and more efficiently, we're focused on the National Lab side on bringing a benefit back to Earth. Now, all of the researchers and scientists that you're going to hear from today, their projects are flying to the space station under the allocation of the U.S. National Laboratory. So all of those researchers, why are they taking their research to space? Why conduct research in space? Well, there are a couple of very unique aspects of doing research in space. The first of those that I'll talk about is microgravity. Microgravity absolutely changes just about everything about your science that you can think of. It's a little bit like looking at your research through a new lens. Fluids behave differently in microgravity. Convection behaves differently in microgravity. And you'll hear a little bit more about that later. Microgravity has profound effects on living systems, everything from microbes to cells to whole organisms, whether we're talking about plants or animals or humans. You'll hear a little bit more about that as well. The space station also affords researchers with an extreme environment. We're able to put research materials outside of the space station where they're exposed to a vacuum, atomic oxygen, a little bit out there, and extreme temperature variations. And we're able to test materials out there to understand something about properties or manufacturing processes, really rapid way of testing rather than doing something on Earth. And so, again, the research that we're doing in space really is research that can't be done anywhere on Earth. The third unique aspect of the space station is its vantage point, with which not only to study our Earth, but to look out further into the cosmos. And you'll hear a little bit more about that as well. This has been a banner year for the ISS National Laboratory in terms of how many payloads we have flown to the space station and how much utilization time we've used. It's been a fantastic year, and there's more to come. There's a couple months left in this year, and we're gonna use every bit. As Pete mentioned, with this being the first Cygnus CRS-2 launch, we're very excited to be taking advantage of this new late load capability. Today, we're loading some of those very last payloads that get on the rocket before launch. And so this opens up the door for a lot of life science research in particular that need that condition, need to be cold or need to be preserved in a way that you can't just sit on a launch pad for a while. One more note about the Cygnus spacecraft. This is designated the SS Alan Bean. And Alan Bean is a former astronaut. He recently passed away. A lot of you know that he was a moonwalker, but maybe not all of you know that he was actually a commander of America's first space station, Skylab. And Pete, you may not remember this, but a couple of years ago, we had an opportunity to give Alan Bean a tour of the mock-up facility, the space station mock-up facility in Houston. And I specifically remember just how curious he was about the types of research that we were conducting on the space station. And it was really enjoyable to see how curious he was about that. We have a video that we've put together that we'd like to show you that highlights just a few of the payloads that are launching. Why don't we roll that video? Quick note, late-breaking news, the Anheuser-Busch company has decided, in assessing their readiness and the resources available on the space station, they're going to wait for the next rocket launch to go, and that's just about a month away. So slight delay for them, but it'll give them a little bit more time to get ready.
So we'll take a few questions. If you have big picture questions about NASA's Program Science Office or the ISS National Lab, raise your hand, let us know. Wait for a microphone, please, so that everybody can hear you. We have one question up here in the front.
Is it determined, like the order of experiments, or how are they prioritized?
I can take that one. So a lot of the experiments have individual constraints. You can't do them until something has happened, or you have to do something before the science would go bad or expire. So we take all of the constraints from each of the experiments, and we kind of roll all those together. And some of that is in our feasibility assessment. Can we launch and support this thing on this vehicle? And then we look at, what is, so when are things going to expire? How important is it to our sponsors, to the people who are paying for the experiment to launch? They give us actually the rankings within their portfolios, and then we integrate those together, and we tell the teams, okay, in this week or this month, here's what we need to do because of the constraints. You guys go figure out how it works best.
I see a question in the back.
I was wondering, what part of the station will the zero-G oven be installed?
I believe, this may not be the most current information, but it's going to be in the U.S. Destiny Lab in an overhead rack. So it's the ceiling for you and I, but for the astronauts, it just happens to be a location. And I believe it's actually pretty close to the potable water dispenser. So it just happens to have a slot back right inside there. Many of the payloads that are designed are kind of modular, and the racks on the space station are modular. So equipment can be removed and replaced with new stuff, and so it's going to be an overhead rack in the U.S. Destiny Lab.
Great, thanks. Let's keep going and get to the science. When we have more time at the end, we'll come back for questions. So thank you, Dr. Warren. Thank you, Pete. Our next investigation that we'll talk about is very exciting, the alpha magnetic spectrometer, and I'm going to let Pete introduce our experts there.
All righty. It gives me great pleasure, and it's a great honor for me to introduce our next speaker. Professor Samuel Ting was born in Ann Arbor, Michigan. He received his Bachelor of Science and Engineering degrees in physics and mathematics and a PhD in physics, all from the University of Michigan. He is the Thomas Dudley Cabot Professor of Physics at the Massachusetts Institute of Technology. Professor Ting has proposed and led several international collaborations in experimental physics, using accelerators in the US, in Germany, in CERN, in Switzerland, and on the Space Shuttle Discovery. Professor Ting, in addition to several other discoveries in particle physics and resulting awards, his work at the Brookhaven National Laboratory and the discovery of a new kind of matter, the J-psi meson subatomic particle, has led to the Nobel Prize in Physics in 1976. Professor Ting is a creator and the principal investigator of the alpha magnetic spectrometer on the ISS, which is searching for the existence of antimatter, the origin of dark matter, and the properties of cosmic rays. The AMS results over its 8-year period in space and 145 billion cosmic ray events have changed our understanding of the cosmos, and they continue to do so to this day. Professor Ting.
Thank you, but you forgot to mention during the 8 years on the space station, I think Michigan most of the time lost to Ohio State. So please have the first slide. Please have the first. Yes, the physics of AMS on the space station can be easily understood to know that we want to search for dark matter, antimatter, origin of universe, and new physics phenomena through study of charged cosmic rays. Charged cosmic ray carries mass, and therefore they are absorbed by 100 kilometers of Earth's atmosphere. So the property of charged cosmic ray cannot be studied underground because it becomes shower. To measure the charge and momentum require a magnetic spectrometer in space. Next slide, please. The space station is ultimate laboratory. It provides the highest energy particles. In the past 100 years, measurement of charged cosmic rays by balloons and satellites have typically 30 to 50% accuracy. AMS is providing cosmic ray information with 1% accuracy. The improvement in accuracy is providing new insights. The AMS results contradict with current cosmic ray theories and require development of new theory. In 8 years, over 145 billion charged cosmic ray with energy up to multi-trillion electron volt has been studied by us. Next slide, please. So one of the items is dark matter. Most of the universe is not observable, and it's called dark matter. A galaxy we see is on the left. If you see the other 90%, could be quite different. Next slide, please. So this is a model of heavy dark matter by series. Next one, please. This is our result. In excellent agreement with the model, but you can see at very high energy, the error is quite large, and that's why we need to carry out the experiment to 2024 as shown in next slide. Next slide, by 2024, and this will the projection of the error, then we'll know where's the other 90%. Next slide, please. Another is cosmic rays. Cosmic ray has two kinds. Primary cosmic rays, like hydrogen, helium, ion, are produced during the lifetime of stars. They are accelerated by explosion of stars. You have proton, helium, carbon, oxygen. Next slide, please. Then there are secondary cosmic rays, lithium, beryllium, boron. They are produced by collision of primary cosmic ray with interstellar media. Next slide. What is amazing, we found out as function of rigidity, which is the momentum per unit charge, in the universe, there are only two kinds of cosmic ray. The primary, like helium, carbon, oxygen, and secondary, lithium, beryllium, boron. If you think about it, it's very, very strange. Cosmic ray exists everywhere, but their property, there are only two kinds. Next one, please. And we have measured a few more, the red one, and indeed, this continues. By 2028, we should be able to measure all the elements in the universe. And it will be really amazing. They behave so simply, only have two kinds. Next one. Another thing is low energy cosmic ray. Before us, low energy cosmic ray is always assumed doesn't change with time. But yet we now see protons between peak and valley change by factor 3. And this is very, very important if you want to avoid radiation damage to you to Moon and Mars. Next one, please. In addition, unexpectedly, we found proton, helium, not only have monthly change, have daily changes. Between minimum and maximum changes 200%. Next one, please. So AMS will continue to collect and analyze data for the lifetime of space station, because whenever precision instrument such as AMS is used to explore the unknown, new and exciting discoveries can be expected. Next one. Okay. There's no more than I can answer questions.
Thank you, Professor Ting. So. And just like it's super important for us to extend the ISS and make use of this awesome asset that we have in space, we need to make sure that we are taking full advantage of the AMS. And to do that, to explain to you some of the work that's going to go on in the next couple of months, I'd like to introduce our next speaker. Ken Bollweg is the AMS Project Manager at the Johnson Space Center in Houston. And as such, he's developed spaceflight hardware for over 32 years. He was the chief engineer on the team that originally did the feasibility study in 1984 to determine if it was possible and feasible to launch and operate these very highly complex and delicate instruments that make up the AMS. Ken has spent most of the last 25 years developing and integrating hardware for the AMS to make sure it successfully and safely operates on launch vehicles and on the ISS. So, Ken Bollweg.
Thank you, Pete. And for the last 25 years, I've been following talks by Professor Ting, which I find very difficult. So the first slide, please. So this is where AMS is on the ISS truss. This is where we're going to have the astronauts going out there from the airlock on their spacewalks to do the repairs. Next slide. There are two cooling systems on it that cools the tracker, a primary loop and a secondary loop. The primary loop components are located on the left side in this picture, as you see, and the secondary is on the right side. Now the primary loop has finally stopped working. It was originally designed to last for 3 years of the AMS life on space station, but since Professor Ting has brought us such compelling science, we're going to extend its life. It's already been running for 8 years now, and we want to make it go to as long as space station is going to operate. The secondary tracker loop is what we're going to cut into on these spacewalks to extend the cooling system life. Next slide. So this shows how the cooling system works. In the center on the left is the tracker. It's the heart of the experiment. We need to pull about 120 watts of heat out of that and bring it to the radiators. So there's a two-phase carbon dioxide pump loop, and you can see the pumps in the upper right-hand corner. Those are the components that are failing. Now, I had an example of a pump, but unfortunately the airline I flew here on decided it needed to go to Oklahoma City instead of here. So that's where it is. So the way the system works, it recirculates constantly, pulls the heat out, rejects the heat to space. If you look at the graph on the bottom, the blue line represents the temperature of the experiment as it is on the outside, so it varies 25, 30 degrees from 1 month to the next, whereas the temperature on the inside only varies by about 3 degrees. On a day-to-day basis, it only varies by 1 degree. Next slide. So this is the new cooling system hardware developed in a collaboration with AMS, the AMS collaboration at RWTH Aachen in Germany, DOE, MIT, and several other institutes. On the left side is a tank of CO2. It holds about 5 kilograms. On the right side are electronics, and in the front, in the foreground on the right, are the 4 pumps. Next slide. And this is what it looks like in its final configuration with all the thermal blankets on it, all the connections, all the interfaces that the astronauts will work with during the spacewalk. On the top of it are 8 training fittings that they're going to use. That's how they connect this hardware to the AMS hardware. Next slide. So this is what the fitting looks like. This is called the AMS Advanced Fitting. It's a fitting designed to interface with the crew gloves and makes it much bigger. Again, I had one of these pieces of hardware too, but it's in Oklahoma. Next slide. This gives an example of the extensive testing we do on it. This tubing it's going to swage on is only 4 millimeters in diameter, a little more than 1/8 of an inch. So we purposely damaged the tubing to go to the extremes to see what can it take, what can it still operate with and still seal. And then we do pull tests on it, thermal tests, thermal extremes, thermal cycle, thermal vacuum. In the lower right-hand corner, we have an astronaut in a spacesuit actually doing connection with the fitting. Also extensive vibration testing. Basically, we test these things way beyond what we expect to see in space so that we know they're going to work in space. Next slide. So at the same time, there's an entire tool team from the Goddard Space Flight Center and from the Johnson Space Center developing dozens of other tools. In fact, there are 29 new tools that have been developed for this spacewalk. Next slide. If I start to explain these, I'll be up here for hours. So these are an example of the 29 new tools, including many other existing tools that have been used in the Hubble Space Telescope repairs, Space Shuttle spacewalks, and Space Station spacewalks. Next slide. So then once we develop these tools, we also train the astronauts on how to do these things, and they teach us a lot of it as well. So we start out with a lot of computer graphic displays like this to figure out where we can get them, where the SSRMS, the Space Station Remote Manipulator System, can actually get to on AMS. Next slide. And then we take that training, that initial work, and then we work with the astronauts in the NBL, or the Neutral Buoyancy Laboratory. That's where they simulate near zero gravity underwater. Next slide. This is an example of installing the new cooling box, as you see here, onto AMS. Next slide. And then we have another system called the Active Response Gravity Offload System. This suspends an astronaut above a mock-up of the payload, and you can see he's right about in the middle of that, and then the cooling system box is right in the middle as well. He's suspended there, and this system moves up and down with his movements. It moves side to side, just like it does in zero gravity. If he pushes off of something, he'll rise up, or if he pulls himself down, it'll come down to him. So this is a very nice way for us to be able to get close and interact with him to understand, what he's seeing and what he's feeling. Whereas in the pool, the only ones that can do that with him are the divers. Next slide. We also use virtual reality systems. This is Drew Morgan in the foreground and Luca Parmitano in the background. These are our EVA astronauts that are performing these. So they use this as another method to develop the EVAs, or the spacewalks, and to train. Next slide. So in the end, this picture was just taken a few weeks ago here at the Wallops Flight Facility. We finished all the pre-flight checkouts. This is just before we turned it over for loading on Northrop Grumman flight number 12. Next slide. There's many other people in the background. This was taken last May during a crew training session at RWTH Aachen University, where a lot of this hardware is assembled and tested. You can see the astronauts in the foreground that were involved with this, as well as Professor Ting right in the middle, along with about 70 other people that were involved with this development. Next slide. So our goal is to see a scene like this in the very near future. In fact, in just a few weeks, instead of having astronauts in the vicinity of AMS on their spacewalks, we're going to have them actually inside AMS working on it. Thank you very much.
Awesome. That's great. Thank you both for such a great presentation. And we will be holding news briefings in the next couple of weeks to give more details about the spacewalks themselves and the science once these tools actually get into space. So now we'll take some questions, but if we do run out of question time, just know that there'll be more opportunities in the future. So microphones here and here. Please wait for a microphone to get to you.
Hi there. Question for Dr. Ting. Does the detector detect ultra-high energy cosmic rays, or is it susceptible to those at all?
This detector detects cosmic ray in a region nobody has reached before, trillions of electron volts.
Above the GZK limit? Sorry, to get technical. Above the GZK cutoff then, or?
Trillion electron volts, 3 trillion electron volts.
Okay.
Yeah.
Thank you.
But the most important thing is, nobody has been there before. There are all kinds of cosmic rays. And before that, in 100 years, there were a lot of theories explaining balloon experiments. When you have a large error, theory can easily explain your data because the error is large. When your error is 1%, it becomes very difficult for the theories to explain. So far, not a single measurement can be explained by existing theory.
Hi, Dr. Ting. I'm Chelsea from Space.com. You mentioned before that the AMS could have research done with it could have an impact on our understanding of the human effects of radiation and protecting against them. If perhaps you and also Ken would be able to speak a bit more as to how data collected with AMS could advance our ability to protect against radiation.
Let me first give you an answer, but ultimately I have to always listen to him.
No, he doesn't.
Before us, most of the people assume cosmic ray does not change with time. The cosmic, when you leave the Earth's atmosphere, leave the Earth's magnetic field, the radiation is 90 rem per year. Lethal dose is about 300 rem, estimated from Hiroshima, from Nagasaki, from Chernobyl. Going to the Mars takes 3 years. 3 times 90 is very close to 300. There's no need to come back if you don't have protection. But what we have found out is there are periods the cosmic ray is very, very low. And then there are periods cosmic ray are very, very high in an 11-year solar cycle. And you want to go to the moon and to Mars during the low period is much, much safer. So this is for a monthly. But recently, we found on daily basis, every day the cosmic ray also changes a great deal. If you want to do a EVA, you want to choose with low radiation period. Now go ahead.
You pretty much covered it.
Jeff, here.
Jeff Faust, Space News. Probably for Ken, if you didn't replace the pump, how long do you think AMS would continue to operate? And if the pump failed, could it still operate, but just with a degraded capability?
So the existing system on AMS right now has 4 pumps, and 3 of them have stopped completely. The last one is still operating on an intermittent basis when we have optimal solar beta conditions. I'm actually rather surprised that they've lasted this long because they were originally designed for only 3 years, and it's been about 8.5 years now. But I would expect that it's a matter of months before we won't be able to operate the cooling system at all anymore.
Hi, Ken Kramer, Space Up Close for both. Professor Ting, could you get useful data if this could be extended beyond 2030? And the repairs that you're going to make, how long do you think the AMS will operate?
Now let him answer first.
So AMS, again, was originally designed for 3 years. It's been operating unbelievably well. This is the only thing that's been a serious problem. The new system that you have that I described will operate until at least 2030. If it's based on the leak test data we've done so far, we expect it'll only last about 400 years.
Well, what about the first question?
Can you get useful data beyond 2030? What could you get if you could extend it beyond 2030?
Yes, as I mentioned an example of dark matter. Our data agrees with the dark matter model, but the agreement is still with large errors at high energies. You want to be sure you have found the origin of dark matter. You want to reduce the errors. Okay. Then there's the issue of antimatter. If the universe comes from a Big Bang, before the Big Bang is a vacuum, nothing exists. So at the beginning, there must be equal amount of matter and antimatter. Now the universe is 14 billion years old. You have us. And where's the universe made out of antimatter? Must exist. And so we indeed have now few strong hint antimatter does exist. The rate is very low, 1 in 100 million. 1 in 100 million is a very small number. And so we want to collect more data to make sure what we see is really from something totally unexpected, totally new. So to extend this just to do routine physics is meaningless. You want to go to a region nobody's been there before.
That's what I'm asking.
Yeah, nobody has been there before. People think it's not possible. So far, AMS have done that.
Thank you.
Hi, Elizabeth from Sci-Fi Wire. Question for Dr. Tang. How do you think that AMS will prove or disprove the existence of dark matter and antimatter in the future?
Oh, you can never prove or disprove. If we found anti-helium, anti-carbon, anti-oxygen, heavy elements, then antimatter must exist. Low mass antimatter, like positrons, antiprotons, can come from cosmic ray collision, produce energy, and energy turn into these light matters. But anti-helium, the mass is so heavy, it cannot come from cosmic ray collision. Must have come from new sources. For dark matter, so far, our data agrees with dark matter model, but the error is large. We want to make sure the error agree with the model to order a few percent. That's what we want to do.
Thank you.
One more question here in the room, right behind you.
My question is, you mentioned that antimatter and the radiation kind of peaks and then dips in a cycle.
No, not antimatter, matter.
Matter.
Yeah.
So is there something, is it in a cycle with the sun? Is it something that is trackable, that we can predict?
No, but none of our results can be predicted by any theory. You know, also, just as a scientist, if you do an experiment, you prove the other people's theory. What you learn is very little. It's when you confront the other theory, destroy the theory, you learn something new.
Hopefully we all learned something new this morning. Thank you very much for joining us. It's okay, it's okay, it's okay, it's okay. We're going to continue the discussion about radiation, actually, with the AstroRad Vest. So our experts joining us now are Kat Coderre, Principal Investigator at Lockheed Martin Space in Littleton, Colorado, and Dr. Oren Milstein, co-founder and CEO for STEMRAD. They have cool show and tell.
Maybe put it like right here. Okay, right in the middle. Yep. Perfect. Okay.
So hello, everybody. This is the AstroRad radiation vest that's going up the station tomorrow. Very excited about this. Now, why a vest? Why AstroRad? Well, astronauts venturing into deep space for the first time since the Apollo missions require radiation protection. And it has not been possible to protect the whole vehicle, or for that matter, to protect the whole person from ionizing radiation. STEMRAD is my company that I founded in Israel. It's a startup company about 8 years ago. And we began with protecting first responders to nuclear incidents. And our innovation was selective shielding. So we're selectively shielding those organs that are most prone to either acute radiation syndrome or cancer down the road. So in developing our space solution, we teamed with Lockheed Martin Space Systems, which are the prime contractor for building Orion, which is NASA's next generation vehicle for taking people back to the moon and onto Mars. It's been a very successful collaboration. It's been an international collaboration between the Israeli Space Agency, our sponsor, NASA, that's Lockheed's sponsor, and also the German Space Agency, which is assisting us greatly in this endeavor. This is the first mission of AstroRad. The next will be on Artemis 1 around the moon. Now, AstroRad is very unique in the sense that it really employs the principle of selective shielding. And in doing so, it's providing augmented protection to those most sensitive organs, such as the bone marrow, such as in the case of the female astronaut, the breast and the ovaries. And across both genders, we're looking at protecting the lungs in a very good way, also the gastrointestinal system. Now, a key challenge to overcome is ergonomics, of course. So not only to protect, have efficient use of mass, but also make it flexible and ergonomic. And here's a sample of the shielding component of the vest. You can see that it's quite heavy. It's really, the vest is going to weigh about 22 kilograms, which in microgravity, we hope will be okay. Now you can see it is dense material, high density polyethylene, embedded in a very flexible textile mesh, creating this almost fluid-like behavior, which we're very proud of. Kat.
Okay, and so why the ISS? What are we doing on the International Space Station? So Oren mentioned that it is a ergonomic experiment. So the vest needs to protect the crew from the deep space radiation environment, but it also needs to be comfortable to wear, flexible enough for them to do their daily duties. If we encounter a solar particle event in deep space, they need to actually be able to go about their daily tasks, exercising, moving cargo, performing science. So we have a series of experiments set up on the International Space Station with several astronauts with the goal of starting with range of motion tests. So we're going to work through different ranges of motion, capture that video, analyze the angles, look at areas where there was restriction. We'll have them do exercise. We'll have them do some daily housekeeping, moving cargo around, items like that that they would do every day in space. So we're really lucky that we were able to partner with the ISS National Laboratory and be able to perform these experiments in that unique microgravity environment that the ISS allows us. So we're going to be able to take the amazing data that we get from the ergonomic experiment on the form, fit, function, comfort of the vest, then pair it with our Artemis 1 data. We have an experiment that will be going up on Artemis 1 at the late 2020, get actual information on the performance in the radiation environment. Combined with those two, we'll be able to improve the vest design and the protection for astronauts in the deep space radiation environment. And then lastly, we'll be able to bring it all back home here on Earth. The things that we'll learn on the ISS, especially, we'll be able to improve protection from the radiation environments of medical personnel and nuclear energy industry personnel. And that's it. Thank you. Questions?
Yes, we will take your questions. So again, here on the left.
Again, Chelsea Goad with Space.com. So I heard you mention in there radiation events. So, while it might be comfortable and a lot, lighter feeling in a microgravity environment, just looking at it, it looks like it might be kind of difficult to move around an all day, every day, just as someone who's never been an astronaut wearing a radiation vest. Sure. So then it's my assumption then from what you said that astronauts in the future, with at least the current model, would be wearing it specifically for high radiation events or circumstances and not every day, all day?
Yes, so currently that's the idea with this vest. We would be using it typically during a solar particle event. And we're able to get some measurements on when those are occurring. I know from an Orion side we have some detectors in the vehicle. And those could last up to a week potentially, maybe more, depending on when we're at. Now, of course, one of the previous presenters did talk and say that the missions would try and be designed during more of those solar minimum events. But these SPEs can happen at any point. So ideally, this combined with, at least on the Orion perspective, we actually have some radiation shelters that we can build up. And so they would be in that shelter or wearing the vest during those events.
I see a question over here.
Hi, Rachel from Trenton Systems. Could you describe a little bit of the functionality and the material which really goes into the most important as far as preventing from radiation, and just describe a little bit of how it was designed and the thought behind that?
You want to take that on?
Oh, sure. Yeah. So really, the principle here is really selective shielding. So making it thicker over those organs that you want to protect, and in doing so, getting the best possible use of mass in space. The material of choice for blocking solar particles is polyethylene, or high-density polyethylene, because it's very rich in hydrogen, meaning it's going to create very few secondary radiation rays upon interaction with a solar particle. On our Earth-based solutions, we're using actually heavy alloys such as lead, which are perfect for blocking photons. So it's really depending on what you want to protect against. Yeah.
Other questions here in the room? Okay, I see a few.
Alan Williams, Zog 43 Sport and Rocketry magazine. Wanted to ask, generally speaking, what level of attenuation are you expecting for someone to be receiving by wearing one of these vests? Say, whole body as opposed to specific areas.
Right. Very good question. So we're looking at total body dose attenuation. We're using the term effective dose in that regard. So the tissues in the torso region have a higher tissue weighting factor when it comes to damages down the road. Give a better punch per kilogram for protecting these organs here in the chest and abdominal region. And that's what we're doing. In the case of a solar particle event, it's going to really depend on the energy of that event. You have higher energy and lower energy events. But on average, we're anticipating to reduce the effective dose by about 50%, which is on par with the onboard storm shelter on Orion.
Hi. My question is actually about that onboard storm shelter that you guys have talked about twice. What is that exactly?
So basically, the idea of, in a simple form, is get as much mass in between you and the particles as possible, and the right type of mass. So on Orion, what we actually do is we take some of the stowage areas, which is actually kind of under the crew seats, and we actually remove some of the items from there, and we actually package things around that area. It is a very cozy space that you could be hanging out in for a few days, but it's pretty effective based on our initial designs, and we've actually gone through and done evaluations with the crew on how we actually build that structure out, and where to route the lines, and making sure that there's enough airflow and they can get to everything they need while down there. This vest would actually augment that, so they wouldn't have to stay in that cozy space for as long. So it's actually a really good asset for the crew. So it'll help them continue to do whatever science they need to do, hygiene activities, while you're actually in the environment.
Awesome. Thank you both.
Thanks, Stephanie.
Thank you.
So we'll be moving on to something maybe a little faster. I'll introduce you to Dr. Alessandro Grattoni, and he is the chairman of the Department of NanoMedicine at the Houston Methodist Research Institute, who will introduce us to the CraigX flight test platform, which is a collaboration between the Houston Methodist Research Institute and Lamborghini.
Well, hello, everybody. I'm very glad to be here today. I will present to you the experiment that we're going to perform on the International Space Station in collaboration with Lamborghini, but I want to give you a little bit of background information before that. My laboratory at the Houston Methodist Research Institute, which is an hospital-based institution research enterprise, my laboratory focuses on implantable drug delivery system for the control, administration of therapeutics for chronic diseases. Chronic diseases entail, for example, cancer or hormone deficiencies. So we are work of implantable system that you can insert underneath the skin and can deliver the drug for a long period of time, for years, for the life of the patient, for as long as needed, really. And they can be either remotely controlled via Bluetooth, or they can actually be just delivering constantly, maintaining a sustained level of drug for as long as needed. So for these technologies, first image, please. We focus on a system that could be also refillable. Of course, many of you may be familiar with other implantable technologies that are available on the market for birth control. Unfortunately, these systems are not refillable, meaning that once the drug is completely released, they need to be explanted through a surgical procedure and then reimplant. A new implant needs to be reimplanted. So we are working, especially in the context of HIV pre-exposure prophylaxis, so the prevention of HIV. We're working on implants such as that one that you're seeing on the image right now that can be transcutaneously refilled. So once the drug is gone, you enter through the skin and you reload the drug delivery system so that it's good to go for other period of time that ranges from months to, again, years. Now, we understood that the International Space Station offers an amazing laboratory and with a unique environment, the microgravity, the radiation exposure, and so forth. And we understood that we could leverage it for developing these technologies. So in collaboration with Chad Brinkley, who is a Prox Ops and also a Chief Space Officer at Hypergiant Galactic Systems, we have formed at the Houston Methodist Research Institute the Center for Space NanoMedicine, which is the first of its kind center that focuses entirely on development of nanotechnology in space for biomedical application down here on Earth. So in the context of that, we started performing research on our implantable system. Next image, please. And we tested this very same implant, this bullet-like device that is very small, you can see as compared to a dime, that was inserted in 40 mice in the Rodent Research 6 experiment in collaboration with Novartis. We were actually testing whether this implant could sustain delivery of formoterol to prevent muscle atrophy from occurring in this test animal. Of course, muscle atrophy occurs in a very, in a very strong manner in microgravity condition, and we use that model to test this system and this drug. And we are actually publishing the results right shortly. Next slide, please. We're also testing this on International Space Station. It will be coming soon on our next launch. This Bluetooth remote control implant that can really allow for telemedicine application, meaning you can treat astronauts while they are in space via the internet and via Bluetooth communication inside of the International Space Station or a spacecraft. But at the same time, you can modulate the drug release in patients down here that may be located in remote geographical areas. Next image, please. You can see an exploded view of the implant and how that works. Now, for developing these devices, we are always looking at new materials, and that where connects us to Automobili Lamborghini. We were extremely pleased when Automobili Lamborghini came to the Houston Methodist Research Institute, to the Department of Nanomedicine, and asked for our support in testing the biocompatibility of their carbon fiber materials. As you know very well, Lamborghini develops a series of different carbon fiber material developed with different manufacturing technologies, including 3D printing, for their cars, for the automotive systems. But they do understand that these materials have properties that can be beneficial for many other applications in the biomedical industry as well as aerospace. And so they came to us, and we are studying the biocompatibility of 20 different proprietary materials for Automobili Lamborghini. And we understood also that with this operation in mind, we could fly some of this material in the International Space Station, which is in the context of the next launch. Next image, please. You can see 3 specimens of the material that will fly on the International Space Station that will be mounted outside on the International Space Station in direct exposure to the sunlight, so the radiation, vacuum, temperature fluctuation, and atomic oxygen. And we will evaluate after a period of 6 months in microgravity how these materials fare in terms of their properties, if the mechanical properties are maintained, if the physical chemical structure is preserved as well. And so this will give us a good understanding of how this material work in an extreme environment. You can also do a kind of a little bit of a parallel between the inside the body environment, which is another extreme environment for many materials, and the outer space. So of course the application would not exclusively be the biomedical field, but would also be for aerospace, the aerospace industry, for a number of different technologies that has to do not only with the automotive industry. So Automobili Lamborghini is extremely excited to collaborate with us on this, and unfortunately they couldn't be with me today presenting this project. But so this is the experiment, and we hope to see what happens in 6 months. Any question?
Questions? Raise your hand, wait for a microphone. Here we go, here's one.
My question, originally it was a SmartX platform, I think you called it, that was going to be sent to the ISS and mounted externally?
Correct.
And that, is that
CraigX.
reusable, that platform?
Yes, absolutely.
Oh.
So this will allow multiple investigators to study different type of materials. So there is let's say, a box that would contain different type of samples, and of course, that can be rotated project after project.
Any more questions? Any questions online for social media? Remember, you can use the hashtag AskNASA to submit your question. Here's another question.
Actually, I know this is probably like a really small question, but because I've suffered with it for so many years, is endometriosis one of the diseases that you're looking into using this device for?
It's not a specific area of research of the laboratory currently, but we are spanning many different diseases, again, from cancer to diabetes, infectious diseases, among others. So the importance of these devices, they can really be applied to numerous pathologies. And we will be partnering with pharmaceutical companies. We are partnering already with Gilead Sciences on HIV. We have worked with Novartis before. And so our mode of action will be partner with pharmaceutical companies and move these devices to clinical fruition as soon as possible. That's our mission.
Thank you.
On my end, so you said it's going to be on the outside of station for about 6 months or so. What's the equivalency of that if you're trying to test something in extreme environments here on Earth, or is there?
Well, I wouldn't consider the equivalent condition down here. Automobili Lamborghini have done a bunch of testing of their materials in the desert in Qatar for stretches of time that span over 2 years or more. So, of course, it's not exactly the same condition, but it's expected that, of course, with the atmosphere in between, even in the most extreme environment on Earth, you cannot reproduce the same type of environment that you have outside of the International Space Station.
Okay, great. Thank you so much for sharing.
Thank you so much.
We have a mouth-watering finale for you. Please meet Mary Murphy. She is the Senior Internal Payloads Manager at NanoRacks, and she's going to tell us about the zero-G oven investigation that's heading to space.
Hi. Well, thank you, everyone. I know some of you were already at the briefing earlier this morning talking specifically about the first experiment that we're actually going to be testing using the oven, but I want to take a quick step back here and talk a little bit about who I am, what NanoRacks is, and how we're going to do that experiment. So my name is Mary. I work for NanoRacks. We are just celebrated our 10-year anniversary, which is pretty awesome in the space industry. When we start a small company, that's always quite a milestone. And we are really looking at what's going to happen once we're through ISS and what's going to happen with those next spaceflight opportunities, what's going to be post-ISS, how will we do these long-duration spaceflights, as some of the other people in the room here have talked about already to you today, is what are we going to do when we're in those experiences, and what are we going to need for those people to have a good experience and to be able to perform all these tasks that we're going to ask of them to do all this amazing science research. So one of the things that came to us as an opportunity was looking at baking in space and looking at how are we going to actually do these food products and other things to actually make people have a comfortable experience for a long-duration spaceflight opportunity. So NanoRacks as a company actually developed this oven in collaboration with Zero G Kitchen, and we are very excited that DoubleTree is going to be the first experiment to actually utilize this technology in space. So what I have for you here real quick is a short video that just gives us a little bit about the hardware that I can talk to and give you a little bit more of an understanding of what is this oven and how does it work. So this is the oven itself. What you have here is one of our engineers, Caleb, displaying that in our Houston office. And he's going through basically the same procedure that the crew is going to do on station. So what he's just done is he's inserted that sample tray into the oven chamber, and now he's going to close it and let it essentially bake for that time that it's going to take for it to actually bake in space. And so this oven started as a very small project, and it's kind of become a whole big thing, because when we first talked about it, we're like, we're not even sure if this is possible. But we'd certainly like to find out, and we'd certainly like to do some research to see what we can do to come up with ideas there. And so, as some of you might know, baking on the ground is pretty well known. Everybody everybody understands how baking on the ground works, but how do you transition that into a microgravity experience? So as you can see, you know, we have the hardware, the oven, we have that cooling rack, and one of the actual things that you've seen in this video so far is actually the sample tray. And if you think about it, on the ground, you put a cookie on a cookie tray, you put it in the oven, and you don't have to worry about it going anywhere, right? You put it on the tray, it stays right where you put it. When you come back, it's still there. But when you actually do that in space, if you just put that cookie in there, you have no guarantee where that's actually going to stay within the oven. So one of the things we actually had to come up with was how to keep the sample for this piece of hardware where it needs to be to get that heat and actually have that experience and get that end result, right? So when you look at ovens on the ground, how many of you guys know how an oven on the ground works? All right, so pretty much everybody in the room understands how an oven on the ground works, right? So it's a pretty basic concept. You put hot air in, you heat it up, the hot air rises, you get this great circulation, and suddenly you've got a great baking experience. You know how to time it, you know how it's gonna work. Well, what happens when you go to microgravity? Well, I'll tell you what, when you go to microgravity, you don't actually have that convection current of the air moving when that hot causes that rising to happen and creates that circulation. You don't get that in microgravity. So you have to think about what are the other ways that we can heat stuff up, and how can we make sure that we have this sample that we're trying to bake work just like your oven here on the ground. Well, it's not quite that simple. It doesn't just work like your oven on the ground. We actually have to pretty substantially change the design of the oven from what you thought about to what it actually is. And so when you saw that imagery, you saw that it's actually a cylinder. So the reason it's a cylinder is because we have all those heating elements arranged around the outside of that oven, so that so the heat can actually come to the center of that and actually be more conducted versus convected into the center of that space, so that we get that good heating quality of the sample within this oven. And so really, this is a fundamentally different piece of hardware than your oven here on the ground, but our hope is that this is actually going to be the first step in figuring out how we actually do this type of thing for future spaceflight. And so this is, again, you know, just a great thing where you think about the simple concept on the ground, and when you take it to space, it actually pretty substantially changes the problems that you have and how you actually solve and come up with a solution for that. And so this is just a really, really great experiment. We're super excited for this first opportunity to actually test this hardware, and we have actually the DoubleTree team here, and we're super excited to be partnered with them. And we're very excited that the chocolate chip cookie gets to be the first thing that we actually bake in space. How many of you guys knew that there was never anything that actually had been baked in space? Okay, so not that many of you. Now, for the rest of you, did you actually think that that's something that actually existed, and they actually had things that were already being baked, and that's actually something that people had available already? Did anybody think that was a thing that okay, well, we had like a couple shy people raising their hands back there. But yeah, so as you heard, you know, as you may realize, you know, a lot of the food on station is really great, and it's come a long way from the very beginning of spaceflight, and some of the meals are actually quite impressive. I've had a chance to taste some of them. They're actually quite good, but it's nothing fresh, right? It's all something that's actually been already cooked, and all you're doing is really reheating it. So this is a really cool opportunity to actually figure out what are we going to do when we can't take all the food with us, when we actually have to come up with, now you've been in space, you took your food with you, but now you got to come up with new food because you've been there for a while, right? So this is really all the things that we're thinking about and what happens, and now we have this amazing opportunity to test it on the ISS, and I don't know about you guys, but I'm super excited to see how it works out. So I guess with that, I'll open it to any questions you guys might have for me about how the oven works, what's going to happen with it, and we'll go from there.
Excellent. I think we have a couple Ask NASA questions, so we'll get started with that and then take questions in the room.
Sure.
Yep. Randy DePasquale on Twitter asks, are there any follow-up experiments planned for the zero-G oven beyond the first batch of cookies?
Sure, so not yet, but the oven is planned to stay on station, so we are super excited to see what that next experiment will be. And I think the results of this experiment will be a really good focus to figure out what is next and what would really be a realistic next experiment.
Great. Question here?
Jean Wright from Space Up Close. Mine's more of a comment. I do a lot of research as a NASA docent, and I have to say, of every experiment we've ever taken up at the space station, this has garnered the most interest because I think it's the most relatable, and who doesn't like a chocolate chip cookie or the way it's going to make the ISS smell?
You know, that's a great comment. I think it's one of those things where, you know, I think everyone loves cookies. I don't think there's a lot of people out there that don't. I mean, there's some preferences between types of cookies, but I think you're right. The vast majority of people, I think, are really on board for the chocolate chip.
Hi, how you doing? John from Countdown Today. I'm just curious, as we're going to be coming up on the 50th anniversary of Apollo 12 and Alan Bean walking on the moon, and it's kind of special that this is taking place, and I'm just curious as to, will the Cookie Monster be making an appearance by any chance? Because as you all know, recently Sesame Street celebrated 50 years as well.
Well, you know, I certainly hope not, because I certainly hope that the astronauts have a chance to enjoy this experiment and hopefully get a chance to have a cookie as well. So I hope there's no Cookie Monster involved.
Hi, I was just curious. It looks like, at least in the video you showed, there was no oven mitt. So how are the astronauts going to handle what potentially might be hot stuff coming out of those ovens?
Sure, they do actually have an oven on station, but it does kind of interfere with how we can see the actual insertion. So for the video, for the demonstration, we did not have them use the glove because it kind of blocks a lot of the view of the sample tray. But there is a glove that's already flying with the oven, so that when the crew actually goes to remove that, they will actually use a glove for that. And then if you'll look actually at the video, they actually have a place next to the oven to actually place the tray once they remove it, so they can actually cool it. And one of the things that I failed to mention that I think is fairly relevant to the conversation we're having right now is that there are some small filters there in that silicon. You can kind of see it there in the imagery that he's taking there now. And that will actually, we believe, allow the opportunity for the crew to actually get, hopefully, a smell of the first baked cookie in space.
Okay, one more question here.
Hi, Chelsea Good, Space.com. So a couple of months ago, when people were first getting really excited about this, about to launch, I heard some discussion around the shape of the cookie and how, all of those chemical reactions that go into baking will actually be affected by the microgravity. And it was said that it might be puffed up or even end up looking spherical. So I'm curious if you have any more ideas or a better grasp on what it might look like, or if we just have to wait and see.
I think, unfortunately, we're going to have to wait and see, but it has been quite the topic, especially amongst the team, about what are we actually going to see when this happens, because we really don't know, right? I mean, when you bake here on the ground, you put the cookie on the tray, it puffs up on the top of the tray, and the bottom is flat, and the top is a little bit curved based on, the ratio of your ingredients. But obviously, nobody's done this in space, so we don't know exactly what this is going to look like. So it could come out more like a cylinder. It could puff up kind of in a general, cylinder type shape. It could actually create a sphere. We really don't know, and I think that's one of the more exciting things that we'll find out when we actually do the experiment.
New meaning to cookie balls.
Oh yeah, quite possibly.
Question in the back of the room.
Yeah, I was just curious. You said there was an oven on board already, and I was curious as to what, are they using a conventional microwave, or is there a conventional oven up there?
Oh, so I'm sorry if I caused any confusion with that. There is actually no oven currently in space. This oven that we're launching is the very, very first that's actually going to go and be in space. When the crew actually prepares food, and there's a lot of information, and Liz probably is your best person to give you a lot of detail on that, but they're looking at essentially heating up what they have. So they have essentially what's called a food warmer, which enables them to basically put the packets of food in there to warm it up, or they're doing things like adding hot water to a bag to actually cause the reaction and get it to be the temperature that they want to eat it. Hopefully that's right.
I think there was one other question over here.
Thank you. I'm going to ask the question everybody's wondering. With NanoRacks developing this system, is there a matching development program for microgravity milk dispensing and dunking systems?
Sadly, I think that's a missed opportunity. But we do have some future-looking next missions, so it's definitely possible that could be something we could look at in the future.
And the astronaut Don Pettit did develop a glass of sorts for use on the space station. So that at least exists as a possibility for a container into which to dunk your cookie.
So there could be a great future collaboration there then.
Another question in the back.
After the experiments have been performed by the astronauts that are required, will the oven be available for their own personal experimentations?
Well, I don't think they're going to have an opportunity to just kind of do their own experiments, but it is something that we are planning to use for future investigations as well. So, of course, if crew members have an idea, they could certainly bring that to us, and we can certainly look at implementing that as well.
They just don't have raw ingredients.
That too.
A couple more in the back.
Hey, was it always cookies? And if not, what else was being considered?
So when the opportunity first came to us, it was mostly a question of, can we actually do this kind of idea of cooking in space? What could we actually do? Was an oven possible? And that's really how the opportunity started. And so when we first started looking at it, we actually had something that looked vastly different from what you've seen today. It was a very tiny experiment, and it was basically, if we put some heating elements in this box and we use this type of power, what could we actually get out of that? And then from there, it kind of graduated to be a more what you see once we kind of understood some of the properties that had to be addressed in order to take that idea of cooking on the ground and make it work in that microgravity environment of the ISS. And then through that process, around the time that we actually had the SpaceX launch with Starman, there was quite an interesting engagement on Twitter. And the Zero-G Kitchen team actually engaged with DoubleTree and actually got them excited about the idea of the fact that they could be the first thing that's baked in space. And it just kind of has gone from there. It's actually been a pretty wonderful collaboration. Because of all the different expertises that these folks and these teams bring together, it's been a really great synergy between all of us in terms of the opportunities that it's brought to the different teams to engage in to be successful in this project.
We have another question here.
Hi, it's a two-part question. One is, how long has the project been in development? And the second, I mentor a women's STEM program. How many women are on your team working on this project?
Those are great questions. So the first question, I think we're probably just past the year mark. I think might be like a little bit longer than that. It's kind of hard to keep track, especially in this industry. Things go by so fast. And for your second question, we actually have quite a good group of women that work in the team. I actually have on my team individually another gal that works with me directly in mission management. We also have Abby, who runs our marketing communications department. And we also have quite a bunch of folks down in our Houston team, especially the team that engaged with the safety process of approving the oven, which is no small feat. As you all know, safety is very important to station and for the longevity of the crew. So I would say a good portion of the team has actually been female, and actually the project manager for the Zero-G Oven project is also a female. So I'm very happy to say that it's been quite a good mix of folks.
Great, thank you. I think that's all the time we have for questions at this time. Thank you so much for joining us. As we've heard today, the space station is an important laboratory because everything behaves differently in space, even cookies. We can increase our knowledge of engineering, of sciences, physical sciences, biology, human physiology, our planet Earth, and the universe itself, right? Several additional science investigations were featured earlier this month on October 17th in a teleconference that we held. If you didn't get the chance to dial in for that teleconference, you can still listen to a replay of it and hear about some additional exciting investigations that are headed to space. The replay of that teleconference is accessible by dialing 1-800-756-6241. Again, that number is 800-756-6241, and the replay will be available until November 16th. Thank you for joining us to hear about the science that's headed up on Cygnus tomorrow. The launch is scheduled for 9:59 a.m. Eastern Daylight Time tomorrow morning, Saturday. And you can tune in today at 2:30 p.m. to hear about the space station status, the status of the rocket and the spacecraft itself, and of course, a launch weather forecast. And then the broadcast of the launch itself will start at 9:30 a.m. on Saturday. Thanks so much. You can continue to follow along with all of the cool science and research on Space Station by following on Twitter at ISS_research and at nasa.gov/ISS-science is what that should actually say. ISS-science. Thank you, and we'll see you again at 2:30.